This will be a walkthrough of the AQA GCSE Combined Science Physics 2023 Higher Tier Paper 1. Question 1. Wind power and solar power are both renewable energy resources used to generate electricity for the national grid. 1.1. Which of the following is also a renewable energy resource? Well, this word renewable is going to help us answer the question. Defining the word renewable means it can be replenished. So essentially, when the energy resource goes down, it can be brought back up. So it can be used again and again and again. So, which one from these lists is renewable? Well, geothermal works by heating water through the core of the earth, which is extremely hot. That can definitely be used again. Natural gas is an example of a fossil fuel, so that's non-renewable, so it cannot be replenished, so it can't be that. And nuclear fuel can't be replenished because it has to be used, then it can run out, so it can't be nuclear fuel. So our answer is geothermal. 1.2. The energy transferred by the national grid in 1 second was 36 gigajoules. Which of the following is the same as 36 gigajoules? So giga is a prefix that we need to be aware of. So we need to remind ourselves what the prefix giga means. Well, we have kilo, which is 1,000. We have mega, which is 1,000,000. So we know that that's going to be 6 zeros. And after that, we will have giga, which will be 1,000,000,000, which is 9 zeros. So that'll be 1 times 10 to the power 9. So if we have 36 gigajoules, that should be 36 times 10 to the power of 9, which is our third option here. Question 1.3. Figure 1 shows how the mean power output from solar and wind energy resources in the UK varied between 2014 and 2019. Figure 2 shows how the power output from solar and wind energy resources varies in a typical year. So let's analyze figure 1 first, and then we'll analyze figure 2, and then we look at our question. So we're given a key. The grey box is wind power, and the darker grey box is solar power. What do we notice? From 2014, there is an increase. Then there is a decrease to 2016. And then there is an increase to 2019. So there's a little bit of a fluctuation between 2014 and 2016. Then after that, there's just a solid increase for wind power. For solar power, you can see that there's an increase from 2014 to 2017. But there is a slight increase from 2017 to 2018. About 2018 to 2019, it remains constant. So, what we're just going to have to do then is we're going to try to see if we can use that in whatever question comes up. Let's look at figure 2. Figure 2, our key again, dashed line is solar power, solid line is wind power. So let's look at solar power first. You can see there's a little bit of a fluctuation. Goes up and decreases. But then when it gets to May, June, July, our power output is highest, and then it decreases down to December. Looks like the opposite essentially for our wind power though. It's decreasing from January and it gets to around June, July, it's at its lowest point, and then it starts to increase again up to November. Then there is a slight decrease again at December. Explain the changes in power output from solar and wind energy resources between 2014 and 2019. You should include an explanation of the change in power output during a typical year. 6 marks. So what they want us to do is explain the changes in figure 1. So what's the reason for these increase and decrease that we see for wind power? But what we need to then do is make sure that we include what happens during a typical year here. So let's just start by stating those changes that we have seen. So we can say that 2014 to 2016 there's a fluctuation, because remember that we're dealing with the whole time period, 2014 to 2019. So we're starting then with our solar power, so we can discuss that first. So our solar power is a general increase from 2014 to 2018, then it remains constant from 2018 to 2019. A typical year though, let's say for the solar power, is that from January to May it increases. So its highest point between May to July, then it decreases until December. So if we really think about it, compare this to our seasons, January to about April is our spring. Then we've got May to August is our summer. And then September to December is our autumn and winter. So you can add on then that for solar power is highest during the summer, and of course at lowest during winter. Now let's explain that then. What would be the reason why there would be an increase as the years go from 2014 to 2018, a little bit constant from 2018 to 2019? Well, what is occurring in terms of a change in this time period? Well, it's going to be due to climate change, because there's global warming that's occurring. So increase between 2014 and 2018 is due to global warming and climate change. Why is it going to be highest during the summer? Because we expect the light to be most intense during that time. But remember also, what is also going to be different during the summer, the days are going to be longer. So we expect to be the light intensity to be higher for longer. Okay, so we've been discussing the solar power. What we can then think about then is, remember that solar power needs solar panels for it to be able to be used. So what would also be increasing during 2014 to 2018 would also be the presence of more solar panels. Okay, let's discuss our wind power now. So what do we notice for wind power? We noticed there was a fluctuation between 2014 and 2016, and then there was an increase to 2019. But in a typical year, as we go from January to July, there's a decrease. It's at its lowest power output in July, and then it increases to December. So let's just state that. Consider there's an overall increase, because it starts off low and then is higher at the end. Now, why might there be a fluctuation between 2014 and 2016? Well, wind is unpredictable. We don't know when it will appear. So there might just be that year, 2015, might have been a bit more windy than the other years. That could be an explanation. Then in our typical year, what did we say? That between January and July it decreases, but then it increases to November. Now, why is there, if we go back to figure 1, why is there a bigger power output when we're comparing the two types of power? Well, it's probably because in the UK, because that's where the question was based on, we're expecting there to be more wind compared to sun. So then we would expect there to be more wind turbines present than solar panels. So that's why there'd be probably a more reliance on wind turbines and wind power than solar. And then lastly, let's look at figure 2. If we compare the two types of power in the summertime, when it's its highest solar power output, it's its lowest wind power output. So when it's during this summer term, we would expect it to be more sunny but less windy. So here is our answer now. And what we've done is we've been describing in these first bits what is occurring during the two graphs. But then what we've done later then is we've explained our reasons for any changes. And in our explanations, we've included both solar and wind, and we've mentioned what happens in a typical year. So we should get our 6 marks by doing those 3 things. Question 2. Body analysis scales use the electrical resistance of a person's legs to estimate the percentage of water in the person's body. Figure 3 shows body analysis scales. So the person puts their foot down, and then it will measure the percentage of water in the human body through resistance. The person's legs contain both solid tissue and water. A student used resistors to model the solid tissue and water. The student connected a 20 ohm resistor in parallel with a resistor R. Figure 4 shows the circuit diagram. So we've got a battery, an open switch, an ammeter, which measures the current, and then we have 2 resistors with one already set to 20 ohms and one R we don't know the resistance of. As it says in the question, the resistors are in parallel, and we can see that in this setup here. 2.1. To determine the total resistance of both resistors, a voltmeter must be connected into the circuit. Complete figure 4 to show where the voltmeter should be connected. Well, a voltmeter is measuring the potential difference. And when we include a voltmeter in any circuit, it needs to be in parallel across the components. So we need to show a voltmeter across the 2 resistors in parallel. So best place to put that would be here. 2.2. A student calculated the total resistance of the two resistors. The student's answer was 26 ohms. Explain why the student's answer cannot be correct. Well, let's go back to the circuit. The total resistance the student calculated was 26 ohms. Why is this not correct? Well, we've placed the resistors in parallel. There is a rule that we have to follow, because resistors can be placed in series or they can be placed in parallel. If the resistors are placed in parallel, then the rule is the total resistance in a parallel is smaller than the smallest individual resistor. So that means then that the total resistance has to be smaller than 20 ohms. Or if it was R and R was smaller than 20, then the total resistance would have to be smaller than wherever R was. Use the physics equation sheet to answer questions 2.3 and 2.4. 2.3. Write down the equation that links current, resistance, and potential difference. Well, this equation is for Ohm's law. So, to find that out, it will be potential difference, which is V, is equal to current, which is I, multiplied by resistance, which is R. 2.4. When the total resistance of the resistors was 7.5 ohms, the current in the circuit was 480 milliamps. Calculate the potential difference across the two resistors. So using our equation, V equals I times R. The resistance is 7.5 ohms. The current in the circuit is 480 milliamps, as we identified before. But that's not our standard unit of current. Our standard unit of current is amps. So we need to convert milliamps to amps. So to do that, it will be dividing by 1000. So that means we need to be 480 divided by 1000, and that should be 0.48. So to calculate the potential difference, it will be 0.48 multiplied by 7.5. So in our calculator, that would give us a value of 3.6 volts. The student investigated how the resistance of R affected the total resistance of the circuit. Table 1 shows the results. Well, here's table 1. The resistance of R is increasing by 5 ohms each time. Our total resistance is also increasing. Some of the results are plotted in figure 5. So we've got a graph. It looks like we have some points missing, and the axes are not labeled as well. 2.5. Complete figure 5. You should label both axes, plot the two remaining values from table 1, draw the line of best fit. So let's do each in order. We're going to label both axes first. Our x-axis should be the first column on our table, and our y-axis should be the second column on our table. So we're changing the resistance of R. So it needs to be that resistance of R in ohms. But then for our y-axis, it needs to be the total resistance of the circuit in ohms. So we've labeled both axes. We need to plot the two remaining values in table 1. So there are 5 values in the table. There are 3 values plotted. Now remember that in our x-axis, each of the values is going up in 5s that we saw in the table. So we're missing a value for 15 ohms and 20 ohms. So we need to find that in the first column of our table. So 15 ohms, our total resistance is 8.6. 20 ohms, our total resistance is 10. So we're going to do 15 first. We need to find 8.6 on our graph. Well, it looks like each line is an interval of 0.2. So 8.2, 8.4, 8.6. So we do our point there for 15 ohms. And then 20 was 10. So you can just place it right there. So from there now, we need to plot our line of best fit because we've done our second point. So we need to draw a line of best fit now. So our line of best fit can be a nice curve going through the points. Two 2.6. What resistance of R would give a total resistance of 4.4 ohms? So we need to find 4.4 on our y-axis. Remember that we said that each line is going up in 0.2. So first line would be 4.2, second line would be 4.4. So reading along to our curve. And then when it touches the curve, we want to go downwards. So doing that, we want to check now what will be our interval between our values on our x-axis. So reading it, it looks like our values, our interval is 0.5. So it's 5, it'd be 5.5 and then 6. So that means our resistance would be 6 ohms. The body analysis scales initially show a reading of 0.0 kilograms. When the student steps onto the scales, the reading is 64.8 kilograms. The student steps off the scales and then immediately steps back on. The scales now show a reading of 64.1 kilograms. 2.7. Complete the sentence. The difference between the two values given by the scales is due to a something error. Well, what it can't be is it can't be a zero error because it was set to 0 and that was a reading with nothing on there. So if it's not a zero error, there is no other reason to explain this change other than it being a random error. Two 2.8. The height of the student is programmed into the scales. The scales place the student into a category A, B, or C based on height and mass. Figure 6 shows how the scales use the category and the total resistance of the legs to determine the body water percentage. So x-axis, total resistance of the legs in kiloohms, y-axis, the body water percentage, and 3 curves, each representing a different measurement. The total resistance of the student's legs is 600 kiloohms. A healthy body water percentage is between 45% and 65%. The different measurements of the mass of the student mean that the student could be in either category A or category B. Evaluate if the student has a healthy body water percentage. So they've given us the value of the total resistance and what a healthy body water percentage range is. So we have to use the categories of A and B to find out if that person is healthy or not. So let's just check. we have to start with 600 kiloohms. So what we want to do is you want to take 600 kiloohms and read up to category A first. And then read along to the y-axis. Now doing that gives us a value of 62%. And let's check again. Is that between 45 and 65? Yes. So that means category A, we can say, will be healthy. Let's do the same for B now. So just continuing on our first line, then reading that along. That gives us a value of 68%. And again, checking our range, it's outside the range now. So that means that category B would be unhealthy. So let's state that as our answer. Category A gives a percentage of 62, so would be healthy. Category B, percentage of 68%, so would be unhealthy. Question 3. Figure 7 shows how the national grid transfers energy from a power station to some street lamps. So what have we got? We've got a power station, and that's connected to a transformer. Transformer now is connected to some transmission cables, which are attached to pylons. And then we go to transformer Y, which is connected to the street lamps. Explain how transformer X increases the efficiency of the national grid. Well, knowing how the national grid works, we should be able to identify what transformer X and transformer Y are. Transformer X is going to be a step-up transformer. Transformer Y is going to be a step-down transformer. Now, what do these mean? Step up means it's going to increase the potential difference. Step down means it's going to decrease the potential difference. So there can be our first point now by identifying what transformer X does. X increases the potential difference. But why do we want to increase the potential difference? Well, the reason is because we want to be able to decrease the current through the transmission cables. So we want the current to be decreased. And to do that, we need to increase the potential difference. Why do we want to decrease the current? We want to decrease the current so there is less current or power dissipated from the transmission cables, as that can happen very easily when the current is higher. But by us decreasing the current and then increasing the potential difference, it will still mean that the power that will reach the street lamps is still fairly high. So there's our second point we mentioned. It allows the current to be decreased. And then that causes less power dissipated from the transmission cables. 3.2. The potential difference across the primary coil in transformer Y is 400,000 volts. The potential difference across the secondary coil is 11,000 volts. The current in the primary coil is 660 amps. Calculate the current in the secondary coil of transformer Y. Use the physics equation sheet. So we need to find the equation from the physics equation sheet that's going to involve potential difference in secondary and primary coils and current in secondary and primary coils. So the equation that we would need to use in this case then would be Vp IP equals Vs Is. So potential difference in the primary coil multiplied by the current in the primary coil would be equal to the potential difference in the secondary coil multiplied by the current in the secondary coil. So what we need to do now is just input those values into our equation. So a potential difference in primary coil, 400,000. Our current in the primary coil is 660 amps. Our potential difference in the secondary coil is 11,000 volts. And we need to multiply that by current in the secondary coil, which we don't know. So rearranging the equation now to find current in the secondary coil, it will just be 400,000 multiplied by 660 divided by 11,000. If putting that into a calculator, we come out with a value of 24,000 amps. (3.3) Why is the current in each street lamp less than the current in the secondary coil in transformer Y? Tick one box. So, which one is going to be most appropriate here? Current is used up in the cables between Y and each street lamp. Well, that's not entirely true. The current is just passing through, so not correct for that one. Some of the current is dissipating to the surroundings. Well, we already discussed this. This is supposed to be lower now because of the step down transformer, and because we use a step up transformer and we've increased the potential difference. So that can't be correct now. The cables between Y and the street lamps have electrical resistance. Well, that is quite true, but the cables would also then mean that so would the coil. So that wouldn't explain the reason why the current is always going to be lower. And this current and the street lamps are connected in parallel. Well, let's think about what would happen if one street light was broken. Then it wouldn't mean that another street light wouldn't be able to work. It would still be able to work as well. So what that's meaning then is that the lamps are in parallel. And what happens in a parallel circuit, the current is shared. So that would explain why the current is always going to be lower. So that should be our correct answer. (3.4) Figure 8 shows the top of a street lamp. A light sensor and lamp are labeled. The light sensor detects if it is day or night. Figure 9 shows part of the circuit in the light sensor. So we've got a battery, a resistor R, and we have this symbol which represents a light dependent resistor. Explain what happens to the potential difference across resistor R as the light intensity decreases. Well, we need to remember how the light dependent resistor works. So if we sketch a graph here, and this graph is supposed to have light intensity against resistance. What will happen is as the light intensity is lower, the resistance is higher, but as the light intensity increases, the resistance decreases. So the question has said to us the light intensity decreases. What's going to happen? Well, the resistance in the circuit would increase. But remember what is going to happen when resistance is higher. Resistance is supposed to oppose the current. So if resistance increases, then the current is going to decrease. Now, if the current decreases, that will mean that the potential difference is going to decrease. Remember that all of these three factors are linked together in this equation here, which is Ohm's law. So if resistance is higher, current is lower, potential difference is going to be lower. When the current in resistance R is 20 milliamps, the power transferred by resistor R is 6 watts. Calculate the resistance of resistor R. Use the physics equation sheet. 4 marks. So, we're using a physics equation sheet to find an equation that involves power, current, resistance. Well, you can use equation power equals current squared multiplied by resistance. So, if we plug in our numbers now into our equation, see how we can rearrange it. So our power in this case is 6 watts. Our current is 20 milliamps. Once again, we're not happy with this unit. We need to convert it to amps, so dividing it by 1,000. So our value of current would actually be 0.02 amps. Remember that we need to square that, and then we need to multiply that by R, which we do not know right now. So rearranging, it'd be 6 divided by 0.02 squared, and then that would equal our resistance. So plugging that into a calculator, we will get an answer of 15,000 ohms. Question 4. A scientist investigated a sample of a radioactive material to determine if it would be suitable for medical use. The method, results, and conclusions of the scientist will need to be checked by other scientists before the results of the investigation are published. What name is given to this checking process? Well, when other scientists are checking people's work to see if their claims are true, are not false, this is known as peer review. 4.2. There is an increased risk of cancer if the scientist is irradiated by nuclear radiation. What property of nuclear radiation causes the increased risk of cancer? Well, cancer is through mutation. Mutation is change to DNA. DNA can be affected, altered by this radiation, but it's due to the property of the DNA becoming unstable due to knocking off of electrons, and that is known as ionizing. So the fact that the radiation can be ionizing is what will lead to there being an increased chance of developing cancer. 4.3. The activity of the radioactive source is the rate at which the nuclei of the source decay. What is the unit for the activity of a radioactive source? So unit for activity is becquerel. If you want to use the abbreviation, it would just be BQ. 4.4. The scientist placed a radiation detector near the sample and measured the count rate. Explain why the count rate is less than the activity of the sample. Well, if we were to draw it, we'd have our sample, which you know is radioactive, and we've placed our detector next to the sample. The question is, why is the count rate going to be less than the activity of the sample? Well, there's no direction at which radiation is emitted. So radiation can emit towards the radiation detector, and then that's what picks it up, so it causes there to be a higher count rate. But radiation could be emitted in the opposite direction, so it will not get picked up by the detector. So that would mean then that some of the radiation that is emitted is not picked up by the detector, and that would explain the question. So first thing that we can say then is radiation is emitted in any direction. So that means then that some of the radiation is not picked up by the detector. 4.5. The scientists recorded the count rate from the sample with the radiation detector at different distances from the sample. Table 2 shows the results. So our first column is the distance between the sample and the detector in centimeters. So we're moving the sample away from the detector. And then our second column is the count rate. And that number is decreasing. So the further we move the sample from the detector, the lower the count rate. If we move the sample 10 centimeters away from the detector, we get no reading, no count rate. Explain which type of radiation was emitted by the sample. So for this question, we need to know about A, the different types of radiation, alpha, beta, and gamma. And we need to know about one of their properties, which is the range in air. Because if we think about our previous picture, what we're doing now is moving the sample further away from the detector. So imagine that this first situation was 2 centimeters. Then we've got another one at 5 centimeters. And then our third situation is at 10 centimeters. We need to remind ourselves then about which is going to have the smallest or shortest range in air. Because at 10 centimeters, it would be too far away from the detector to get picked up. So the one that's got the shortest range in air is most likely going to be the correct answer here. So the way it works then, from our different types of radiation, is gamma has the longest range and alpha has the shortest range. So we should be able to make the conclusion that alpha radiation is what was being emitted. And then our reasoning is that the alpha radiation can't travel 10 centimeters. As it has the shortest range in air. Four point six. The scientist moved the detector closer to the sample and started a stopwatch. The scientist measured the count rate from the sample at different times. Table 3 shows some of the results. So we've got the time in minutes, 0, 30, and 60. And then we've got the count rate in counts per second. At 0 minutes is 1,568. 30 minutes we don't know, so X. And at 60 minutes, an hour, is 98 counts per second. The scientists realized that 30 minutes is a whole number of half-lives. Calculate the value of x in table 3. So let's read the sentence again. The scientists realized that 30 minutes is a whole number of half-lives. Well, it doesn't say that it's one half-life. And remember what the definition of half-life is. It's the time it takes for a radioactive sample to decay by half. So what we would need to do then is find out how many half-lives this sample has. So what we want to do then is find how long it takes to get from 1568 to half of 1568. So let's try and find out what 1568 divided by 2 is first. Well, if we do that in our calculator, we get 784. So 1568 to 784. We know now that that is going to be one half-life. What we want to do here is you want to try and find out how many half-lives is it going to take to get to 98. Because if we can get to 98, then we can find out our time period from there. So 784 divided by 2, that would give us 392. So we know now that that's our second half-life. And then dividing 392 by 2, we get 196. So that will be our third half-life. And then 196 divided by 2 would give us 98. So we now know that to get from 1568 to 98, that is 4 half-lives. So 60 minutes is 4 half-lives. So if we think now from 30 to 60, that's just multiplying by 2. So that would mean then that 2 half-lives would have passed to get from 30 to 60. So we just need to find out then what would be the number when it's 2 half-lives from 4. Well, jumping up 2, that would take us from 196 to 392. So that would mean then that our value of x will be 392. .7. The scientists had a second sample of the radioactive material. The scientists made appropriate measurements, then calculated the half-life of each sample. Why was the half-life calculated from the second sample slightly different from the half-life calculated from the first sample? Tick one box. Well, the numbers are different. What would cause the numbers to be different? Radioactive decay is a random process. That is absolutely a true statement. So let's check our others first. The count rate from a radioactive sample is predictable. Well, it's unpredictable, so it can't be that. The samples were at different temperatures. That won't affect the half-life. And the size of the sample was different. Well, in terms of the size, that could not affect the half-life. So a correct answer is the first one.